Analytical definitions of monotonicity on an interval. Hello everyone. To begin, let's reflect on our previous lesson. In the previous subsection, we explored the visual behavior of functions by looking at their graphs, which gave us a good intuitive sense of how they move. However, while graphical intuition is a great starting point, mathematics requires a more precise and analytical way to describe whether a function is rising or falling. This formal study of the direction of a function is known as monotonicity. In this subsection, we will move beyond the visuals and define the formal mathematical conditions under which a function f is considered increasing, decreasing, or constant over a specific interval, I within its domain. This will provide us with the rigorous foundation needed to prove these behaviors algebraically, which we will dive into in the coming slides. 1. Increasing functions. Now that we have established the need for a precise, analytical approach to monotonicity, let us move from the visual intuition we discussed previously to our first formal definition: increasing functions. To begin with the general concept, a function is said to be increasing if, as the input value increases, the output value either increases or remains the same. Let us look at the formal mathematical definition. A function f is increasing on an interval I if, for all x sub 1 and x sub 2 belonging to interval I, the condition that x sub 1 is less than x sub 2 implies that the function value of x sub 1 is less than or equal to the function value of x sub 2. To make this easier to apply, let us break this down into a step-by-step process. First, pick any two numbers, x sub 1 and x sub 2, from within the interval I. Second, ensure that x sub 1 is the smaller of the two values, meaning x sub 1 is less than x sub 2. Third, calculate and check the corresponding function values, f of x sub 1 and f of x sub 2. Finally, if you find that f of x sub 1 is less than or equal to f of x sub 2, then the function is classified as increasing. It is important to notice that because we use the less than or equal to sign, this definition allows the function to stay flat for some time. In the next slide, we will explore a more stringent version of this concept known as strictly increasing, where the function is forbidden from staying flat. 2. Strictly increasing functions. Now, let's move on to a more specific type of growth: strictly increasing functions. While we just discussed that an increasing function can either rise or stay flat, a strictly increasing function is more restrictive. In this case, the output value must increase whenever the input value increases. There is no possibility of the function remaining constant or staying flat. Let's examine the formal definition. A function f is considered strictly increasing on an interval I if, for all x1 and x2 belonging to that interval, whenever x1 is less than x2, it necessarily implies that f of x1 is strictly less than f of x2. To help you visualize this, let's look at a real-world example involving compound interest. Imagine a bank account where interest is compounded daily. In this model, let x represent the time in days, and let f of x represent the total balance in the account. As time progresses, which we represent as x1 being less than x2, the balance always grows because interest is continuously being added. Since the balance never stays the same and never drops, the value of f of x1 is always strictly less than f of x2. This makes it a strictly increasing function. Now that we have a clear understanding of functions that rise, we will move forward to explore the opposite behavior: decreasing functions. 3. Decreasing functions. Now that we have established the definitions for increasing and strictly increasing functions, let us turn our attention to the opposite behavior: decreasing functions. A function is said to be decreasing if, as the input value increases, the output value either decreases or remains the same. Essentially, the function is either heading downwards or staying flat as we move from left to right. Let us examine the formal definition. A function f is decreasing on an interval I if, For all x1 and x2 belonging to interval I, the condition that x1 is less than x2 implies that f of x1 is greater than or equal to f of x2. To help you apply this definition in practice, let us go through a step-by-step breakdown. First, pick any two numbers, x1 and x2, from the interval I. Second, ensure that x1 is the smaller value, meaning x1 is less than x2. Third, determine the corresponding function values, f of x1 and f of x2. Finally, if you find that f of x1 is greater than or equal to f of x2, then the function is classified as decreasing. Keep in mind that this definition allows for the function to stay flat. In the next slide, we will refine this further by discussing strictly decreasing functions, where the output must always drop. 4. Strictly decreasing functions. Having just discussed decreasing functions, let us now examine the concept of strictly decreasing functions. While a decreasing function allows for the output to remain the same, a function is strictly decreasing if the output value must decrease whenever the input value increases. In other words, there is no possibility for the function to stay flat. Formally, we define it as follows. A function f is strictly decreasing on an interval I if, for all x1 and x2 belonging to interval I, whenever x1 is less than x2, it necessarily implies that the function value of x1 is strictly greater than the function value of x2. To help you visualize this, let us consider a real-world example involving a depreciating asset, such as the value of a new car over time. In this scenario, let x represent the age of the car in years, and let f of x represent the market value of the car. As the car gets older, meaning as we move from a smaller time value, x1, to a larger time value, x2, the market value typically drops. Since the value of the car at year x1 is always higher than the value at year x2, we can say that f of x1 is greater than f of x2. This is a perfect example of a strictly decreasing function. Now that we have covered both increasing and decreasing behaviors, we will move on to the final and simplest type of monotonicity, the constant function. 5. Constant functions. Now that we have discussed functions that either rise or fall, let us examine the third possibility, the constant function. Simply put, a function is constant if the output value does not change, regardless of what input value you provide. Looking at the formal definition, we say that a function f is constant on an interval I if f of x equals c for all x in the interval I, where c is a constant real number. In other words, no matter which value of x you choose from that interval, the result is always the same fixed number. To help you visualize this, consider a real-world example, a monthly subscription fee for a streaming service. If we let x represent the day of the month, the cost, f of x, remains exactly the same whether it is the first day of the month or the 30th day. For instance, if the fee is $10, the output is always 10, making it a constant function. With this, we have covered all the primary types of monotonicity. In the next slide, we will summarize these definitions in a table to help you distinguish between them more easily. Key takeaways. Now that we have explored each definition individually, let us consolidate our understanding with this summary table. This table provides a side-by-side comparison of the different types of monotonicity we have discussed, assuming that we have picked two values where x1 is less than x2. First, let us look at increasing functions. As we saw earlier, the condition here is that f of x1 is less than or equal to f of x2. This tells us that the function's behavior is to either rise or stay flat. Next, we have strictly increasing functions. Notice the subtle difference in the condition. Here, f of x1 must be strictly less than f of x2. This means the function always rises and is never allowed to stay flat. Moving down to decreasing functions, if x1 is less than x2, the condition is that f of x1 is greater than or equal to f of x2. In terms of behavior, this means the function either falls or stays flat. Similarly, for strictly decreasing functions, the condition is that f of x1 must be strictly greater than f of x2. This ensures that the function always falls. Finally, we have the constant function. Here, the condition is simply that f of x1 equals f of x2, which means there is no change in the output value regardless of the input. Please take a moment to study this table carefully, as these precise distinctions are crucial. In the next slide, we will discuss some common mistakes students make when applying these specific conditions. Common mistakes. Now that we have covered the definitions and the summary table, let's discuss some common pitfalls to avoid when applying these concepts. First, be careful not to confuse increasing with strictly increasing. It is a very common mistake for students to use these two terms interchangeably, but in mathematics, there is a critical difference. Remember that an increasing function allows for the graph to be flat or constant for some parts of the interval, which is why we use the less than or equal to sign when comparing the function of x1 to the function of x2. In contrast, a strictly increasing function forbids any flat sections. The output must always rise, meaning the function of x1 must be strictly less than the function of x2. Second, pay close attention to your inequality signs, especially with decreasing functions. A frequent error is writing that the function of x1 is less than the function of x2 when describing a decrease. To avoid this, always remind yourself that for a decreasing function, the output for the smaller input, x1, must be larger than or equal to the output for the larger input, x2. Therefore, the correct analytical statement is that the function of x1 is greater than or equal to the function of x2. Finally, never ignore the interval. As we established at the beginning of this section, monotonicity is not necessarily a global property of a function, but is defined over a specific interval. For example, a function might be strictly increasing on one interval, such as from 0 to 10, but then switch and become strictly decreasing on another interval, such as from 11 to 20. Because of this, you must always specify the interval, denoted as capital I, whenever you are stating the monotonicity of a function.